Have you ever written some code and it just felt sluggish, slow, or maybe it crashed because it just gobbled up way too much memory? Well, the secret to fixing that isn't just writing better code, it's about handling your data in a smarter way. Today, we're opening up the programmer's ultimate toolkit, data structures. This stuff right here is what separates pretty good code from truly great, efficient software. So you always hear about this, right? Why are all the big tech companies, from Amazon to Meta, so completely obsessed with DSA in their interviews? It's actually pretty simple. Every single tap on your phone, every search you type into Google, every item you toss into an online cart, all of that is data. And how you manage that data is the difference between an app that feels lightning fast and one that's just frustratingly slow. And this quote, it really gets to the heart of it. Look, anybody can store data, but the real skill, the one that gets you hired, is organizing it so that your applications are fast, responsive, and don't hog resources. In the world of software, efficiency is king. It's everything. Okay, so let's start with the absolute basics. Imagine raw data is like a super messy, chaotic room. You can't find anything, right? It's useless. To actually make it useful, you've got to bring in some furniture, some shelves, some kind of organization. You need to give that chaos structure. So here it is, our formal definition. A data structure isn't just a container for data, it's a system. It's a very specific method of arranging information in your computer's memory to make accessing it and working with it as efficient as humanly possible. Now, when we keep saying efficient, what do we really mean? Well, it pretty much boils down to two major things. First, speed, making our programs run faster, which gives a way better user experience. And second, memory, using up fewer of the computer's resources, which is absolutely crucial when you want to scale up and handle lots of users. But hold on, before we start building all these cool structures, we need a plan, right? You need a blueprint. And in the world of programming, that blueprint has a name. It's called an abstract data type, or ADT for short. So an ADT is all about the concept, the big idea. It defines a set of operations, basically what you can do with the data. It's like saying, hey, I need something that can hold a list of my friends, and I need to be able to add new friends and maybe remove some. It doesn't care how you write the code, just what it needs to be able to do. And this slide lays it out perfectly. The ADT on the left, that's the what. It's the conceptual blueprint, the wish list of features. And the data structure on the right, that's the how. It's the actual code you sit down and write in Python or Java to bring that idea to life. All right, let's grab our first proper tool from the toolkit, the incredibly flexible linked list. Now, unlike something like an array, which needs one big continuous block of memory, a linked list is all about making dynamic connections on the fly. It all starts with this thing called a node. Think of it as a little box. Each node holds two things: the actual piece of data you care about, and then a pointer, which is basically an address that points to the next node in the sequence. You just create another node somewhere else in memory, and then you tell the first node's next pointer where to find it. Just like that, you're forging links in a chain. Okay, so here's the trade-off, and you really gotta get this. Linked lists are amazing. They're superstars when you need to add or remove elements all the time, especially somewhere in the middle. You just have to rewire a couple of pointers. But they do have a weakness, and that's searching. If you want to find something, you have no choice but to start at the very beginning and follow the chain, one link at a time, which you can imagine can get pretty slow. Now for our next tool, and I promise you, you use this one every single day without even realizing it. It's called the stack. Its whole principle is super simple but incredibly powerful. Have you ever hit undo to fix a typo, or clicked the back button in your web browser to go to the last page you were on? Well, congratulations, you've used a stack. Every time you visit a new page, it gets placed on top of a pile. Clicking back just takes that last page right off the top of the pile. A stack works on a very simple principle called LIFO, last in, first out. The best way to picture this is a stack of plates at a buffet. You can only add a new plate to the top, and you can only take a plate from the top. The last one you put on is always the first one you take off. And the operations for a stack have these special names. When you add an element, you push it onto the stack. When you remove that top element, you pop it off. And if you just want to see what's on top without actually taking it off, you peek. Push, pop, peek. Simple as that. Okay, so now let's look at the complete opposite of a stack. If a stack is all about reversing the order of things, our next tool, the queue, is all about fairness and making sure things stay in their original order.
Think about this. If you and 3 of your coworkers all send a document to the office printer at roughly the same time, how does the printer decide which one to print first? It doesn't print the last one first. That would be fair. It prints the document that got there first. That, my friends, is a queue in action.
The guiding principle here is FIFO, first in, first out. And the perfect real-world example is just a line, or a queue, for movie tickets. The first person to get in that line is the first person who gets to buy a ticket. It's fair, it's orderly, it's a queue. And just like stacks, queues have their own lingo. When you join the line, you in-queue yourself at the very back. When you finally get to the front and it's your turn, you de-queue from the line. It's that simple. You add to the back and you remove from the front. So let's just put them side by side to make it super clear. A stack is LIFO, last in, first out, like a stack of plates. It's perfect for things that need reversing, like an undo feature. A queue is FIFO, first in, first out, like a ticket line. It's perfect for handling tasks in an orderly way like printer jobs. And there you have it, our starting toolkit. You reach for a links list when you know your data is going to be changing a lot. You grab a stack when you need to manage things in reverse order. And you use a queue when the order of arrival is the most important thing. Now, we've really only just scratched the surface here, but you now have the fundamental building blocks. So the next time you use an app and it feels a little slow, you won't just see a problem, you'll see a potential data structure challenge. The real question is, which tool are you going to choose to build a better, faster solution?